much. So let's continue from where we arrived last time. So last time we saw that generalizing the Wilbein and spin connection formalism of gravity, we could combine all higher spin fields into one form. So I'm just recalling what I said last time. Into a one form function of space-time and some auxiliary twister-like variables such that this big field has an expansion in y and y bar. Let me write it down first and then remind you what the notation means. Okay, so we expand this big field into powers of y and y bars. Here the notation is supposed to, it's a condensed notation such that this object here has n alpha type indices and m alpha dot type indices. So this means y alpha 1, y alpha 2, y alpha up to y alpha n, and the same for Bark. And so if we restricted this to be bilinears in y and y bars, this would describe Wilbein and spin connection. In general, the term which has s minus 1 powers of y and s minus 1 powers of y bar, it's like a spin s Wilbein. And the whole collection of terms such that the sum of powers of y and y bars is 2s minus 1, with n going from minus s minus 1 to s minus 1. This includes generalization of spin connections. So the term with n equals 0 is this, which is the Wilbein, and all the other terms included here are spin connections. So for spin 2, it's just E and omega. For higher spins, there are more general, more spin connections, more auxiliary objects. Okay, so so in this space y and y bar, we introduce the star product. And the same for y bars, such that bilinears in y's and y bars generate SO3,2 under star commutators. And the algebra of general functions of y and y bar is the higher spin algebra, which generalizes SO3,2 to an infinite dimensional algebra. And this W is to be thought as a gauge field for that algebra. So what you should keep in mind that these y's and y bars are like the gauge group generators. So this is like a Young-Mills gauge field for the algebra generated by these y and y bars under this star product. Okay? All right, so because this is a one form here, we see that this contains spin 1, spin 2, spin 3, and so on. It cannot contain spin 0, because even if we have no y's, this is still a one form. There is still an index here. So there is no spin 0 in this big field, but we expect that the theory that we are looking for, this higher spin theory in AdS4, should include a scalar field. We know that from the point of view of CFT, there is a scalar operator in the vector models, which is like phi I, or psi bar psi in the fermionic version. So we need a scalar. So you can expect that this field will not be by itself enough to describe the full equations of motion. We need some other field which will include a scalar field. Okay, so this other field will be indeed a scalar, Vx, and it will again depend on these auxiliary variables. So we need another big field, which usually Vasiliev called master fields. So these and these are called master fields because they encode all the fields of the theory into a single field. So we need this other object, which is a scalar. And the bottom component of this object will be the bulk scalar field. But as we will see, this will contain also more things. Will contain the curvatures associated to those gauge fields, as we'll see later on in this lecture. Okay, so if you want to write down free equations of motion for higher spin fields and scalar in AdS, these two objects will be enough. Indeed, historically, Vasiliev first started from here and wrote down some linearized equation for free higher spin fields. But if you want to go to nonlinear theory, you have to introduce some more machinery. Okay, so unfortunately, I have to introduce more machinery. So it turns out that to write down the full nonlinear theory, we have to do something more, enlarge our variables even more than this. Okay. So in the nonlinear theory, well, this may not be the unique way to do it, but this is the way that Vasiliev solved the problem, writing down interactions for these fields. He suggests that we should enlarge our space of fields more than this, and first of all, double the twistor variables. So from y and y bar, we enlarge our auxiliary internal space and double it. Okay. So there is no real way to prove this. So you should just, for now, accept that I'm postulating some of the elements of Vasiliev theory, and then we'll see that after everything is postulated, we can write down some nonlinear equations, and then we can see that they are consistent and they describe higher spin fields. So first we do this, we double twistor variables, and so we allow all these fields to depend now not just on y and y bar, but also z and z bar. Okay. And this z and z bar will also satisfy, will also have some star product analogous to that one. So this big space now has a star product such that, well, the y's stays the same, and then we have non-trivial star contraction between y's and z's. Let me go here. So this, in particular, implies that y's and z's, by this definition of star product, commute on the star product, but it will be important that they do have a non-trivial star contraction. The commutator is 0, but there is a non-trivial star contraction here. Okay, this is important when you study the actual equations. Okay, so the full star product on general functions, let's see if I can fit it here, on general functions of y and z, can be represented as a integral, generalizing the one I wrote last time just for the y space. Okay, let me write it, condense it this way. Okay, so here the big Y and big Z is a shorthand notation to include both Y and Y bar, and the same for big Z. And this big U is again shorthand notation for u and u bar. So this guy is actually small. Okay, so this is u alpha v alpha, u bar alpha dot, v bar alpha dot. Okay, this is definition. This defines the star product in this space for all possible functions. In particular, it gives this on commutators of y and z's. Okay. Okay. One property of this star product is that it admits a special object, which is usually called the Klein operator. And its complex conjugate. Okay, so just an exponential built on z and y. This object satisfies, which you should check as an exercise, k star kappa is equal to 1, and the same for bar. And on functions of y and z, it acts by switching the dependence on y and z. Okay. All right. And one last property which will become useful later is this one. All right, so I'm sorry I have to introduce a lot of machinery today, but bear with me, and after we introduced all of this, we will be able to write down Vasiliev equations. So summarizing, we first have to double this space and introduce some star product in this bigger space, which is given there. It reduces to the one I introduced last time on z-independent variables. But it's more general, okay? Now, when you thought I introduced everything, actually there was still something missing. We still need one extra ingredient to write down Vasiliev equation. Yes? There is no star, yes. There is no star. Okay. So this space is completely auxiliary. In the end, we will project everything to functions which are independent of this. And to do this enlarging of the space in a consistent way, Vasiliev found out that you need yet another field, which is a gauge field in those auxiliary directions. So you need to introduce a gauge field in these directions, and then there will be an enlarged gauge symmetry associated with it, which will allow to basically, in the end, gauge away those directions. And this extra field is usually called S. Maybe since I don't have space here, I write it here. So one more field that we need is S, and Y and Z. And this S is one form in this auxiliary space. Okay? And otherwise, these components, as all the other fields, depend on X, Y, and Z. Okay? So we have a one form in space-time. This will end up including the actual higher spin fields. We have one scalar, which will include the scalar field and some curvatures. And then we have this extra object, which will be completely auxiliary. It doesn't have any degrees of freedom inside. It's just needed to write down the full equations consistently. Okay. Any questions so far? Yeah. Say again. S, yeah, all fields depend on everything. So this depends on Y bar, Z bar. Okay. Okay. well, from what I said so far is not completely clear, but this is facility construction. Intuitively, you enlarge this space, but these extra directions are completely auxiliary. In the end, you want to get rid of them. You have some extra gauge field along those directions, which is this S. And then, well, the presence of that S will allow you to write down the consistent equations and, in the end, reduce to physical fields. Okay. Okay. So just that, so that you have in mind, just to repeat what I said, so that you have in mind, in the end, what are the fields that actually contains the physics. The prescription is that, so the physical fields are obtained by projecting down to z and z bar equal to 0 parts of all these big fields. Okay, so this at z equals z bar equals 0 will be that field that I introduced last time, essentially. And this field will include the Wildbeins and spin connections. So in other words, the higher spin gauge fields. And the B, again, after we project it to 0, this component, which is independent of Z, will be the scalar field and the curvatures. So these are the gauge fields. Here is the scalar plus curvatures. So they are not independent from this. They are just derivatives of these gauge fields. And then this extra object is there just to write down equation consistently. And once you project it out to z equals 0, this is just 0. Okay, so it doesn't include any physical fields. Okay, so this projecting out to 0 is not trivial because of the star products here. So, for example, if you encounter y star z, and then you have to take z equals 0 at the end, that's not 0 because of this. Okay, so that's why the z is a non-trivial part of the story, even though at the end you project it to 0. Okay. All right. Let's see. I'll go here. Okay, so we want to now use these fields and write down a system of equations which has some gauge symmetry, and we want to show that it will describe higher spin fields. So let's first postulate what are the gauge symmetries, which are the natural ones. And then we'll try to write down a system of equation which has these symmetries. So W is supposed to be a gauge field, and we saw last time how it's supposed to transform. There is a parameter which depends on these variables. Now in the fully nonlinear theory, it will depend also on these z's plus commutator. Okay. And S, it's also supposed to be a gauge field. It's a gauge field along Z, so it will transform like this. Where this d big Z means that there is both dz and dz bar here. Okay, so don't confuse this Z with the Z of Poincare coordinates of AdS. They have nothing to do with each other. Okay, this Z is this internal auxiliary space. Okay, and then B. So this is now another ingredient that for the moment you have to accept. It's one of another of those things of Vassiliev theory that when first people see it, it looks strange. So you would think that B should just be some adjoint field, transform like an adjoint field. That's almost true, except that we need some kind of twist in this transformation law, where this pi is defined such that pi on a function of y, y bar, z, z bar, gives f minus y, z minus y bar, z bar. So, sorry. I'm sorry. It gives minus y, y bar, minus z, z bar. And this can be represented using that Klein operator like this. Okay. Okay. So it's a twist. This is called a twisted adjoint representation. If it was a adjoint representation, there wouldn't be this pi there. There would just be commutator of B with epsilon. Okay. It will become maybe slightly clearer later why we need this twist. Okay. But let me just tell you that if you don't do this, you will find a system of equations at the linear level which is empty. There are no propagating degrees of freedom. Okay. All right. So notice that because this can be represented as epsilon, kappa star epsilon star kappa, then, and because kappa square to 1 under star product, that means that the field phi, which is B star kappa, is a regular adjoint. Okay, so you could in principle write down Vassiliev equations in terms of this field instead of B, but the physical fields are more easily read off from B. And so traditionally the equations are written in terms of B, not of phi. Okay. Any questions so far? So there's a lot of ingredients that I introduced today. Unfortunately, there is no real derivation of why we need all these things, except that in the end we'll see that the equations are consistent and describe what they should describe. Yes? That's also equal. It's equal in the case that we're interested in. So in the case that we're interested in, all these fields are even in the internal variables because we're describing bosonic theories. So in bosonic theories, this is also equal to kappa bar f kappa bar, because these functions are supposed to be even if you change the sign of all the y's and all the z's. This is true in bosonic Vassiliev theory. Yeah, thanks for the question. So indeed, we need to have an extra constraint that W, S, and B are even functions of the internal variables. Otherwise, we would be describing also half-integer spins in this expansion. Okay. Okay. Any questions before I write down the equations? Okay, so here is the equations. I just introduced one last notation. I promise it's the last one. So it's convenient to combine, and it's natural to combine W and S into a single gauge field, W plus S. So this gauge field is a one form both in X and the ZZ bar. And so then it transform as it should transform. where this d here includes both dx and dz. Okay? Okay, then the equations that Vasiliev proposed, which are invariant under these gauge symmetries, are the following. Okay, so these are the equations. Now it's straightforward to check that they are indeed invariant under these gauge symmetries, because we're just using standard language of Yang-Mills theories, and so you can see that this object here transforms as an adjoint. This object here is a function of B star kappa, it transforms as an adjoint, and this pi here is because B is postulated to transform in that way. Okay. So far, this function is an arbitrary function. Okay. So far f is arbitrary. The system is consistent for any function. Okay. Any questions about these equations? Yes? I mean that, well, it's gauge invariant, and the two equations are consistent with each other. For example, this one can be seen as the Bianchi identity for this equation. If you apply d to this equation, you get, again, consistent with itself, and so on. So it's a self-consistent nonlinear system of equations with a gauge symmetry. Okay. Now, it's not at all clear at this point that this describes higher spin fields, of course. So we still have to do some work there. Yes? Here. So far, f is arbitrary. F, yes. F can be any function of B star kappa, and this would be a system of gauge invariant and self-consistent nonlinear equations describing the dynamics of these master fields. We don't know yet why this is related to higher spin. Well, we have a hint because we started from something which was a way to encode higher spin fields into one form, and then we enlarged and finally reached this system. But you have to do some work to show that there are higher spin fields inside. Yes?
Is it somehow clear that this is the most general?
There is no proof, but it seems that, well, I think there is no proof. But within, if you want to write down an equation which has here curvature of A equal to something, then this something here has to be some two form. And basically from the knowledge of what you should get in linearized equation, you see that this two form should only be in this auxiliary space, and that field redefinitions allow to throw away terms which involve z and z bar, and so on. So there is no proof, but within this framework, it seems that the structure is quite rigid. Okay?
Can you take limit v equal to z bar equal to 0 now?
And, well, what do you mean by, so you're supposed, so these are equations, you're supposed to solve them, and then once you have some solutions, you can read off the physics by projecting to z and z bar equal to 0.
Yeah, but can I project it for you?
So by itself, you wouldn't know how to do it. Like, the star products involve those integrals, so you have to do some perturbation theory around some simple solution, and then you know how to do it. We'll do that in an example. Okay. But before we do that, okay, let me write down here let me write down here a less condensed form of the equations, which is useful to see at least once. So that's very compact. We can expand it a little bit in terms of W and S. So the equations look like this. There is one important feature that in terms of W, these equations say that W is flat, and then you get all the other equations. It's a simple exercise to just get this from that. It's trivial. But I'm writing them in this form because I will need them for linearized analysis. Okay, so these and these are equivalent. I just written down in this way. Okay, so there is one feature of these equations that you may be surprised about, is that they are first order in derivatives with respect to space-time. There is only dx, right? There is no second derivative, but we know at the end of the day we are supposed to describe propagation of some fields with a second derivative kinetic operator, right? So this is a feature of this formalism of Vasiliev, which is called unfolded formulation, technically. It just means that you write down a system of dynamical equations in terms of just first order equations, but introducing a lot of auxiliary fields. And the second order equations will arise after you eliminate those auxiliary fields. So just to give you an idea of how this works in a toy model, in a much simplified example, so that you understand how it works, let's open a parenthesis and describe the Klein-Gordon equation in flat space in a similar way, in this unfolded formulation where you have first order differential operators only. Where can I do that? So here is a toy example, which is Klein-Gordon in flat space. This is almost trivial, but it illustrates some points. So suppose we take massless Klein-Gordon in flat space. We want to rewrite it in a form which is of this type, where we only have first order differential operators, but some tower of auxiliary fields. So we do something similar to what we are doing there. Let's introduce some master form, master field, which is a function of x, and some internal variables y, so that this will have an expansion. Now I'm assuming these y's to be not twistor-like, but vectors. Okay, so I have an expansion like this. I want to have a 1 over n factorial here. And this just tells me how many powers of y comes along with this, and these are functions of x. Okay, so I'm just writing down some generating function. Okay. And then I claim, well, it's a very simple claim, that the Klein-Gordon equations are equivalent in terms of this, are equivalent to the following system. So there is one dynamical equation which has one derivative with respect to x, and one constraint equation which doesn't have x derivatives, which is this. Okay, so this constraint just means that these components are traceless. Because if you take this, you will get a eta mu nu here, which get a trace. So this constraint just means that I work with traceless stuff, and this is my equation. Okay, so showing that this is equivalent to Klein-Gordon is very simple. You can probably already see it. But let's do it. So basically, this shows how you work with those type of equations. What you do once you have this type of equations, you expand it in y's, and then you get equations, you group equations in terms which have the same number of y's. So that will be a chain of equations for all those fields inside this big field. So you start from the bottom one. The bottom one will tell you that dx mu phi 0, so the bottom term, which has no y's and y bars, this must be d dy, sorry, this must be phi mu 1, okay, because, so put that expansion inside here to get, so if you extract from here the term without y, here the term without y will be the one involving phi 1, where these derivatives gets rid of one y. Right? So you get that. That's the first equation. And if you go on to the next level, you get this must be equal to this. Okay. And now, if you use the constraint that these phi's are traceless, take the trace here. So, and here you use that phi mu is d dx mu of phi 0, you get that, so take trace of second equation, you get this. So you get that the bottom component of this field is just a Klein-Gordon field, and the higher components are just derivatives of that Klein-Gordon field. Okay, so they are not new dynamical degrees of freedom. They're just they are expressed in terms of that. Okay? If you can go on, if you go on, you don't get anything new. You get that all the higher ones are derivatives of the bottom ones, and the bottom ones satisfy this equation. Okay? Any questions about this? Well, you mean just one charge scalar and a gauge field. That would be some nonlinear version of this story, which would be similar to this. So for the claim is that for any system of dynamical equations, you should be able to do this. Whether you can do it in practice depends case by case. I'm not sure for the case you're asking if it was done or not. So this is an example of a nonlinear version of that. I don't know if it was done for just a gauge field coupled to a charge scalar. Okay. All right. So to make contact with the Vasiliev formulation, and just maybe to motivate why in 4 dimensions is useful to use this y alpha dot instead of just y mu's as I was doing here, is because that is a way to automatically impose certain tracelessness constraints. So notice that here we could alternatively impose the tracelessness of this object by declaring that the y's are null. If the y's are null, then if there is a trace inside this object, it will just be projected out from this field because y squared to 0. So in 4 dimensions, we can solve such a constraint in terms of these twistor variables. So in 4D, we could replace y mu by y alpha, y bar alpha dot. Okay, and then we could just work with a master field function of y and y bar, which is more similar to the Vasiliev construction that I was doing, where this says alpha 1, alpha n, alpha dot n, sum over n. Okay. So if you do this, the tracelessness of this object is automatic. It becomes the statement that this object is symmetric in the alphas and the alpha dots. And then you can write down the same Klein-Gordon equations with just one condition, which is this. Okay. So this is totally equivalent to that, except that you can impose directly the tracelessness by working with these twistor-like variables instead of the vector-like. Okay. And so, well, I will leave it to you to check that this gives again Klein-Gordon, but it's almost obvious. Okay. Okay. One feature here of this kind of equations, which also appears in the Vasiliev equations, so let me comment about it now, is that typically the equations relate derivatives with respect to space-time to derivatives with respect to the internal variables. And in the Vasiliev formulation, we have this star product, which essentially, for general functions, it will be equivalent to having as many derivatives with respect to y and z's as you can, right? So if the equations relates derivatives with respect to x to derivatives with respect to y, that means at the end of the day that there are higher derivatives interactions in this system. Okay. And we've seen also last time that we indeed expect that there are higher derivative interactions. For example, there should be a higher derivative cubic coupling of the graviton if we want to reproduce the right stress three-point function of the stress tensor. So these are expected features. Okay, so let's go back to the equations now. Let me use this blackboard. So can I erase this Klein-Gordon? Okay, so I wrote these equations. So far, there's no background assumed here. They are completely background independent. It's not clear where is AdS, right? So where is AdS? But from the discussion of last time, you should be able to guess where is AdS. It will just be a particular maximally symmetric solution of this system of equations. What is this solution? Well, it's just P equal S equals 0, and W equal just a bilinear in Y and Y bar. I hope you don't mind if I omit indices here, just to be quick. So if you take these ansatz where B and S are 0 and W is just a bilinear, plug it into those nonlinear equations. Of course, everything becomes trivial except this, except the first one. And the first one, just to give you that dE plus omega wedge E is equal to 0, and d omega plus omega wedge omega plus E wedge E is equal to 0. Okay? So this is vanishing of torsion, and this is the equation that describes AdS solution. It tells you that the Riemann tensor is related to the product of the metric, essentially. Okay? So this is AdS. So we don't start with by assuming that there is an AdS solution. The formalism is background independent, and AdS is just the simplest solution of these equations. Okay, yes? Well, there is a scale here. I mean, you can restore scales by dimensional analysis, right? But that's the only scale. There is no other scale. So in particular, when you start to write down interactions, because they are higher derivatives, by dimensional analysis, you will have powers of this radius to compensate the derivatives. And the limit in which the radius go to infinity is not well defined at the interacting level. Yes?
The formulation of this theory requires Princeton variables, which only exist in certain space dimensions.
Yeah.
Is the purpose of it just to impose the faceless condition automatically, or does this formulation only exist in certain dimensions?
This exists only in 4 dimensions, but there is a formulation in general dimensions. I'll mention it a little later. You can work with something like, instead of twistor internal variables, vector-like internal variables, like the y mu's that I was writing for the Klein-Gordon example. But then you have to impose some constraints. So in 4 dimensions, it's very convenient to use this because certain constraints are automatically imposed. Vasiliev wrote down a similar system of equations in general dimension, but they don't involve these twistors. They involve some vector-like internal variables. Any other question? Okay. Okay, so AdS is just a very simple solution of this. Notice that for this solution to exist, we don't need to know anything about this f here. Okay, this could be arbitrary, except that it should not be singular as we set b equals 0. So this is a solution for any of these systems. Now, before we go on, let's pause to discuss about this f, because so far it looks like we have a very large family of possible higher spin theories where parameterized by this choice, which is completely arbitrary at this level. Okay. So is it possible to restrict this? So not go through the argument, but let me just say that by field redefinitions, you can somewhat restrict it. You can restrict this f. Now, by this x, I just mean the argument of f, which is v star kappa. You can restrict it to be of this form. It's traditionally written in this way, where this phase starts with a constant, then there is a quadratic term, quartic term, and so on. Okay. So, in fact, this f is not completely arbitrary, but there is still a large amount of freedom. It can be put in this form. Okay. So we still have a very large family of possible Vasiliev theories. But there is one more ingredient which allows to restrict this even more, is if you impose some, if you require that you have some parity symmetry. Remember that in the 3-dimensional case, we have this free fermion and free scalar theory. They are both parity invariant. We don't have any other CFT which is parity invariant and has exact higher spin symmetry. So we would expect somehow to not have such a big amount of theories, but only 2. And these 2 theories arise if we impose parity symmetry. So I'm here. Parity. So if you impose that there is, if that the system of equation is invariant under parity transformation of this type, then you see that there are only two solutions. The two solutions depend on whether you postulate that this B is even or odd under parity, this scalar field. We have two choices. We can take it to be even or odd. So the first solution, if B is parity even, then condition is that f of x is equal to f bar of x, and that leaves you with the only possibility fx is equal to x. So this is called the type A theory. Which I only mentioned in the previous lectures. I said that there is this type A theory, and it's the one supposed to be dual to the scalar vector models. So this type A theory, it's a special case of this general system if you impose a parity symmetry and if you impose that B is parity even scalar. And then there is another, the other choice if B is parity odd, then the condition is that f of x is equal to f star of f bar, I was calling it there, f bar of minus x. And then here we have fx is equal to ix, and this is the type B. So this is dual to the fermionic vector models. And the type A to the bosonic, to the scalar vector model. Okay. So in each of these two theories, you have a choice of delta equal 1 or delta equal 2 boundary condition. So you can describe either the free or the critical scalar, or the free or critical fermion here. Okay? Okay, but in general, if we relax parity, if we don't require that our higher spin theory is parity invariant, then we do have this larger family of theories parameterized by these choices. So f is neither x or ix. It's this general thing with a phase. And these more general theories were conjectured to be dual to these vector models coupled to Chern-Simons gauge fields at the boundary. Okay, that's what I mentioned last time. Those theories break parity. It turns out that they do have approximate higher spin symmetry. And, well, let's say a little bit later, that at least at the level of three-point function, this proposal seems correct. So the general Vasiliev theory, which break parity, may be dual to Chern-Simons plus vector model at the boundary. Okay. Any questions about this? Yeah. Well, it will be another solution. It will not be AdS. I don't know if this solution exists. It's not, yeah. Well, so you will just have this to be 0.
So the two bottom equations,
This, right.
you only have
Right. Yeah. I think in general, well, it's a more general solution. I don't think it was studied, yes. If you impose that these fields are only bilinear, then I think you get to S equals 0. But there may be more general solutions in which W and S are not bilinear. And they will describe some other solution. Indeed, this is a topic that is very far from well studied. Topic of finding exact solutions of these equations. There are very few exact solutions known of these equations. So AdS is clearly one. There are other exact solutions. For example, there is a solution by Didenko and Vasiliev in which all the fields are turned on and which is asymptotically AdS, and far away, close to the boundary, it looks like the profile of the fields is like a charged black hole. But not much is known about more than that, about that solution. There are other very few solutions. So finding exact solutions of these equations is kind of a not very much explored topic. So I didn't see this one that you're asking about discussed anywhere. It may be that it ends up being equivalent to just AdS, or it may be that there is something more there. I don't know. Yes, well, in the end you want to extract what is the metric of the space, and that will be contained in W. But if S is non-zero, it's possible that the metric of W is not AdS, it's something more complicated. Okay. So this shows where is AdS, but where is the dynamics of the higher spin fields? So to show that this system of equations really describes propagating higher spin fields in AdS, you have to start from this solution and do perturbation theory over this solution and see what the linearized field describe. Okay, so so you do perturbation theory. So you can study small fluctuations around this vacuum. After you have realized that this is a good vacuum of your theory, then you start do perturbation theory on top of it. So you start with a perturbative expansion. Okay, where this is the vacuum, AdS. And 1, 2 denotes the order in perturbation theory. So if you linearize these equations around this W naught solution, you get this. Let me just restrict to type A for simplicity. So this function f, I'm just taking it to be B star kappa. And finally, okay, this d0 tilde is the covariant derivative with the pi twist. Okay. So these are the linearized equations which you can get from here. So if you expand, the first one will give you the derivative of W1 with W0 as term in the commutator, and the others come one by one from these. Okay. This does not move. So you see already at the linearized level, it's quite it looks quite complicated to extract the dynamics. And I will not give you all the details, but just roughly tell you how you proceed to solve these equations. So, well, first let's start from the easy one. You start from here. This equation just tells you that a linearized order B1 is not a function of z and z bar. It's just a function of y and y bar. Okay? And then this already will give you an equation for B1, just in the physical space without z's. Okay? Then here, from here, so this one tells you that B1 is only a function of y and y bar. Once you know that, you can plug it here and solve for S1 schematically. I'm just being very schematic. There is an explicit expression for this solution here. Once you know S1, then you go back to these two equations and try to solve for W. Okay? So remember that in the end of the day, we are interested in the z-independent part of W. So we will split W into a term which is independent of z and the term which is z-dependent, such that this is 0 when you set z equals 0, but it's needed for your equations. And then once you do that from here you can solve for this W prime in terms of S1, which you got from here. And once you know W prime, you put it back here and you get the final equation, which looks like this. So you see the initial equations looked, it looks like W, well, W is a flat connection, but that does not mean that the physical part of W, which is what I called here omega, which is the z-dependent part, that is not a flat connection. So if you go through the machinery, you get that this defines what omega is. There is a non-trivial right-hand side which comes after you work your way through the star products because of the z-space, okay? Okay, so the end result is that the linearized equations look like this. Guess I did. Let's call this one. Just to be consistent. So linearized equations look like this. So this is what you get from those equations at the end of the day for the physical fields projected into z equals 0, which are omega 1 and B1. Okay. Now the problem now is to show that these equations are equivalent to Fronsdal equations and Klein-Gordon for a scalar. So that was shown by Vasiliev before he wrote down the nonlinear equation. So historically, he first figured out how to write Fronsdal equation in this kind of first order looking form around AdS. And then he worked his way through, tried to generalize this at nonlinear level, and he found that the right way to do it was to introduce that z. So here I didn't follow what the history was. Historically, this was found first. And then he showed that the nonlinear equations give this back. Okay? So shown by Vasiliev that this is equivalent to Fronsdal plus Klein-Gordon. let me just, so I'm not going to do that in detail, but just some simple examples. Okay. So if you analyze these equations, you see that they don't mix all components of these fields together. There are some decoupled sectors, one for each spin. And the equation in particular makes what you expect. They mix s minus 1 plus n, s minus 1 minus n, with b 2s plus m b m 2s plus m. So for any s, there is those equations. So those equations split into a system of independent equations for each s, where these components of omega, which should be related to Wilbur spin connection, are related to these components of B. And the equation essentially says that these B are like Weyl curvature tensors of omega, and omega are the gauge fields. So the simple example of that is spin 1. At spin 1, then this equation, so the spin 1 part of omega is just a part independent of y, and this equation just says that the omega let me see how to write this in the most better notation. It says that the omega is this. Plus Cc. So this equation is just a definition of the curvature of the gauge field. This is like a mu, and this is like f alpha beta, the self-dual part of the field strength, and here the complex conjugate will include alpha dot beta dot. So the first equation is just as the purpose of saying, of defining, well, identifying B with the curvature of A. And then the second equation will give you the actual dynamical equation for the spin 1, which is this. Which is just this written in two-component spin notations. Okay? So that's a simple example for spin 1. If you go higher in spins, the story is similar. This equation tell you that this is the, well, for spin 2, you find that it is literally the usual Weyl tensor in terms of the metric which is hidden here. And this just gives you Bianchi identity for the Weyl tensor. And if you go higher in spins, you get the Fronsdal equations for the gauge fields here, and B is just related to derivatives of the Fronsdal fields. Okay? And what about the spin 0? I didn't discuss the spin 0. Well, the spin 0, it just comes from this equation alone. Okay? So that's somewhat the easiest case. Spin 0. This comes from here, which, just to be more explicit so that you get maybe a better feeling of what that derivative is. I think you cannot read this, so I'll write it here. Okay, that last equation there, if you write this derivative explicitly in terms of the W naught, gives this. And this anti-commutator here is due to the pi twist. The fact that you don't have commutator but anti-commutator, this comes from the pi. And that pi now here become important at this level. If you didn't have that pi, This will be a commutator, and then this equation will not describe Klein-Gordon. So more explicitly, this so doing a similar thing to the Klein-Gordon in flat space that I did before. You get this chain of equations. This is similar to what I had before in flat space, except that here I had a regular derivative, and I just had this term here with the double derivatives of y. This is the generalization that you get if you have a non-trivial omega naught and d naught coming from the AdS background. And the fact that you get this double derivative here comes from this anti-commutator. So you can verify that if you take anti-commutator with star product, and remember that this comes with y and y bar. This gives this. And if you didn't have this, but you had the ordinary commutator, this system will just be empty. Okay, so this is, in practice, an explanation of why you need this pi twist. You need this pi twist to get this anti-commutator here to get the right Klein-Gordon equations. So this is a chain of equation for all n. You do the same thing that I did in flat space. You solve one by one, starting from n equals 0, n equals 1, and so on. So after you unfold that, you get to this for the bottom component. Okay, so this is left to you as an exercise. It's not as simple as the one in flat space, but if you want to try to dirt your hand with Vasiliev theory, you should at least try to reproduce this Klein-Gordon equation from the linearized analysis of Vasiliev and show that from here, if you do this unfolding procedure, which is what I described in flat space, you end up with an equation for the bottom component, which is Klein-Gordon. And this is the value m squared equal -2, which I always mentioned in previous lectures. It comes just from the structure of these equations. It's not a free parameter. It just comes from how the equations are written, and you get this value of the mass. Okay? Any questions? Back reaction of in this perturbative? Well, this is a vacuum. It's a maximally symmetric space. I don't think there can be an instability. I mean, you can consider. So here I'm doing perturbation theory with small fluctuations above AdS. You can consider big fluctuation. That means you find some different solutions of this system. Some, like for example, black holes or some kind of solutions with non-trivial profiles. So that would be back reaction of fields which are not small. There are big fluctuations over AdS. Some of those solutions may be, yes? No, it has not been studied, but I find hard to believe that will happen in this theory because, well, if it's true that it's supposed to be exactly dual to these free vector models, I don't see what this instability could mean. Yes.
You can read off value of CLS. Can you also read off G? Or in other words, we've said that.
Can we also read off? Sorry, say again.
Can we read off the value of Newton's constant?
Not from here. Yeah, so there is no Newton constant here in the equations of motion. So the Newton constant will appear once you have an action. If you have an action, then Newton constant will be in front of it. But the equations, that they don't involve, the classical equations don't involve Newton constant. Yeah.
This might be another version of the previous question, but when you do your perturbative expansion, what's the small parameter in which you're perturbing? You're dropping the radius of AdS.
Yeah, well, you assume that these are small fluctuations above AdS. So if you do calculation of correlation functions, the expansion parameter is basically the strength of the source at the boundary point. So you do an expansion in powers of this source. So this will be, for example, calculation of second order correction to these equations above AdS. The first order I was describing, well, I didn't set a boundary condition there, but when we do AdS CFT, we'll do an expansion such that phi's go to some, well, they correspond to some source turned on in the boundary, and then you do an expansion in power of that source. Any other question? Yeah.
In the Klein-Gordon point boundary, is it any way to write on the Klein-Gordon action in terms of phi xy?
Yes, there is a way to write a Klein-Gordon action. It was been done by in a paper by Vasiliev and one of his students, I believe. I can give you the reference later. I can't write down the action here, but it has been done. So
That doesn't help writing down
the higher spin action. Well, that was the hope, but it doesn't help so far. So, yeah. So as you know, one big open problem is that we don't really understand this action well. There have been some proposals, but I think it's fair to say that they are not very well understood. For example, it wasn't shown, or it appears to be not true, that if you expand those proposed actions around the AdS, you get ordinary quadratic actions for Klein-Gordon, Maxwell, and so on. So that would be an order 0 check that you should do on any Lagrangian if you get it. And this has not been checked. Okay. How much more time do I have, Chiara? 5 minutes. Okay, so once you do this perturbation analysis, you can, of course, go on. So as I already mentioned there, you can go to second, third order, and so on. And so that's what you should do. For example, if you want to compare correlation functions in a CFT to some Witten diagrams in this theory. So for example, if you're interested in computing 3-point function, you need to know the cubic coupling in this Vasiliev theory, which means that you have to solve the equations to second order. Okay. So here I did the linearized analysis. If you solve the equations to second order, that will tell you what is the cubic coupling in your theory, right? So in principle, there isn't any obstruction in just working out this procedure and extracting what is the local cubic vertex for these three fields. But in practice, that's not very easy to do. And what we did to compute 3-point functions was not to extract this cubic vertex, but to solve directly the equations of motions. So we solve equations of motion. So we solve the diagram I wrote before, where this schematically is meant to be a second-order field in Vasiliev theory sourced by two boundary points, two boundary sources here, which correspond to two boundary currents inserted there. And once you have this solution at an arbitrary point in the bulk, if you bring that point to the boundary, that sending z to 0, that will give you a 3-point function. So I don't have time to describe this. But you can do this in Vasiliev theory. It's a complicated calculation. You extend what I did to second order. You read off the solution for the master fields. Here, phi is just a schematic. So from the master fields, you know how to read off the physical fields. They should be contained into B and omega. So B is the curvature and omega is the gauge field. You can use either one. In practice, it's easier to use B, the scalar. Once you've solved for that, you take this boundary limit and you get some 3-point function. Okay? So what we checked is that this 3-point function in type A and type B does agree with the vector models, both in the free and critical case. And then one can also do the calculation in those more general theories with parity invariance, and there, sorry, with parity non-invariance. And there you get, well, I think I don't know. And there you also get agreement with what you expect in the Chern-Simons theories coupled to vector models. If you identify those phases to be function of the 't Hooft coupling in the Chern-Simons theory. So maybe I'll just write this down and then, yeah, okay. So remember we had this, in this general theory, we had this phase, which is theta 0 plus theta 2. And if you work perturbatively around AdS, only theta 0 affect 3-point functions. And then from Vasiliev theory, you get this structure. You get a decomposition in 3 terms, where this is the 3-point function in a free scalar theory, this is a 3-point function in a free fermion theory, and this is an extra term which is parity breaking. So that's what you get in the general case. So if theta 0 is 0, which corresponds to type A, you just get this. If theta 0 is pi over 2, which was that I that I had for the type B, you get this. And in general, you get this structure. Okay? And this is precisely the structure that you get in these vector models coupled to Chern-Simons. You can see that by, it was shown by Maldacena and Ziboyedov that you do get such a structure if you use the slightly broken higher spin symmetries of the theory at finite lambda. And it was also then, so that fixed the structure up to some arbitrary function of lambda, which is related to this theta naught. Then explicit calculations actually in the CFT fixed what this function of lambda is. And the end conclusion is that comparing Vasiliev to CFT, we have that theta 0 is supposed to be pi 2 times lambda. What is this? And this will be dual to Chern-Simons plus scalars. Or theta 0 is pi 2 1 minus lambda. This will be dual to Chern-Simons plus fermions. So if you make this identification of the phases with the lambda in the gauge theory, so lambda is n over n plus k for the Chern-Simons theory, UN Chern-Simons theory coupled to these vector models. If you do this, the triplet function agrees. And then the structure of this suggests something interesting, that these two theories seems to be mapped to each other if you exchange lambda to 1 minus lambda. So this suggested some new non-perturbative duality between theories of Chern-Simons coupled to scalars and theories of Chern-Simons coupled to fermions, where weak coupling in one theory is mapped to strong coupling in the other theory. And if you look at what this lambda to 1 minus lambda does, it's just level rank duality. So this is a generalization of level rank duality when you have matter coupled to Chern-Simons. And this is an interesting result in the CFT, which was sort of, well, the motivation to study this initially came from studying higher spin theory. It was sort of inspired from higher spin theory. So it's one interesting result in CFT, which came from studying this AdS CFT duality of higher spins. And this has been checked beyond correlation functions also at the level of thermal free energy. So you can calculate the thermal free energy of this model and this model, and they are mapped to each other by lambda to 1 minus lambda. So this so far seems to be true, but more checks would be needed here. Okay. I think I already took more than 5 minutes, so if you have more questions, you can ask me later. Thank you.